How did Pluto and Charon meet? We discuss this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. The question of how Pluto and Charon, or Charon, formed their close-knit, tidally locked system has long puzzled scientists. This week, Adeene Denton from the University of Arizona returns to explain her team's new modeling that suggests a kiss and capture may solve this mystery. Then Bruce Betts, our chief scientist, joins me for a look at contact binaries in our solar system and a new random space fact in What's Up. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Today we're exploring the outer reaches of the solar system, revisiting a world that continues to surprise us, Pluto. NASA's New Horizons mission flew by that system in 2015 and gave us our first close-ups of that fascinating dwarf planet and its surprisingly complex system. What we saw was not just a cold, distant rock, but a dynamic world with vast plains of nitrogen glaciers and a surprisingly large moon, Charon. Pluto has 5 moons in total, but Charon is so large compared to Pluto that they're often called a binary system. Charon is about half the diameter of Pluto, which is really unusual considering that planets' moons are usually much smaller in comparison. This odd couple, orbiting each other at about 16 Pluto radii, has presented scientists with a really fascinating puzzle. How did they form? And what processes led them to this really unusual configuration, where Charon is not only really close in size, but also orbiting very close by and in a rather circular fashion? To help us unravel these mysteries, we're joined today by Dr. Adeene Denton, lead author of a new paper that revisits the formation of Pluto and Charon. You may remember her from our 2024 episode called Splat or Subsurface Ocean, the mysterious positioning of Pluto's heart. Adeene is a researcher at the Lunar and Planetary Laboratory at the University of Arizona. Her work modeling the collisions of worlds offers a fresh perspective on the giant impact theory that once was the primary explanation for Charon. Her team's new paper, which is published in Nature Geoscience, is titled Capture of an Ancient Charon Around Pluto. It presents a new scenario called a kiss and capture, where Charon was captured relatively intact, retaining its core and most of its mantle. It suggests that Charon might be as ancient as Pluto and has some really interesting implications for other binary systems. Welcome back, Adeene.
It's so great to be back. Thank you for having me.
Well, we last spoke in October 2024, and we were talking about the formation of Sputnik Planitia and the region on Pluto that people sometimes lovingly refer to as the heart. And while we were having that conversation, you mentioned that you were doing this research on the formation of Pluto and its largest moon, Charon. So I was really looking forward to having you back on this. So just to set the scene, what makes the Pluto-Charon system so intriguing?
Ooh, so many things, but I'll try to stay on topic. So, what makes Pluto and its largest moon, Charon, really unusual is that they're kind of similar to the Earth-Moon system. So, I'm going to use the Earth-Moon system as an analog because most of us are more familiar with it. The Earth's moon is weirdly large relative to the Earth. And the entire system has a lot of angular momentum. It's just kind of strange, right? And many people think that the reason we have such a large moon, and compare it to, say, the moons of Mars, right? Mars has 2 moons and they look like little potatoes and they're 0.0001% of Mars's mass. The moon is an actual reasonable amount of the Earth's mass. And it also shares a lot of chemical similarities with the Earth, which is something we only discovered when we got Apollo samples back from the moon. But the easiest way to explain all of these unusual characteristics of the Earth-Moon system is if the moon formed from a giant impact. If something came in early in the solar system's history, collided with the Earth, and then ... the moon formed out of that. And so when Charon was discovered in the late 1970s and was found to be like half the size of Pluto and 12% of its mass, people started to think, that's very similar to the Earth-Moon system. It really makes you think. And what it really makes you think is, did that also happen for Pluto and Charon? Well, in the early 2000s, researchers took the first initial swing at simulating that impact. So basically had a Charon-like body come in and hit Pluto and see if you could capture Charon as a moon and found that, yeah, you can do it. So since then, the going theory has been that Pluto gets Charon in a giant impact early on in the solar system as well.
Which is a cool thing to be able to compare what went down with our system with what went down out there. But there are some clear differences, both in the size, in the composition, and in the fact that these are large icy bodies we're talking about out there. And the ratio of mass between them is significantly different from what's going on with Earth and the moon. So there's got to be some other weird things going on here.
Yeah, it's a little bit different. As you say, the Earth and the Moon are made of rock and metal, and Pluto and Charon are thought to be made out of rock and ice. This is probably the case based on their densities and their sizes, and we assume that they differentiate, so you get all the rock in the center and all the ice on the outside. But again, we don't know much more than that. If that's the case, then it's possible that the fact that they're made of completely different materials could influence how the collision shakes out. But yeah, the other piece is that Pluto and Charon are much smaller than the Earth and the Moon, and they're less massive. So that could also change the collision. And those differences are what led us to do the research that we wrote up in the paper to look at how much does the composition and the size differences between Pluto and Charon affect the impact outcome.
Because in the situation of the Earth and the moon, it was a rather violent impact, right? Is that a similar scenario that we're thinking for out there? Because I think that outcome might be a lot different.
It was not a good time to be on the Earth or what we call Theia, the proto-Mars-sized object that hit the Earth. Because both bodies are much more massive, we think that the velocity at which they collide is basically related to the escape velocity of the system. It's not like when an asteroid hits the Earth. When an asteroid hits the Earth, asteroids are usually much smaller than the Earth itself, right? So the defining factor of the collision is the Earth's gravity. And so you can guess an average speed at which asteroids are going to hit the Earth, and it's tens of kilometers per second, which is pretty fast. When it comes to collisions between bodies that are similar in size, so planets hitting each other in this case, the speed at which they collide is related to the escape velocity of the system. So basically, their combined masses will dictate the speed at which they collide. And because the Earth and the Moon are much more massive than Pluto and Charon, yes, it's pretty violent of an impact. We think there's a lot of vaporization, a lot of melting. The Earth ends up with a magma ocean. The Moon might be partially vaporized and has to recondense, and then it has a magma ocean. It's a mess. Pluto and Charon might be a little bit different because, like we said, they're smaller and they're less massive. So the escape velocity of the system is at least an order of magnitude smaller. I'm talking they're colliding at maybe 1 kilometer per second, which might sound fast to you if you think about it, but that's slower than a fighter jet. We go faster than that. So it's actually a lot more gentle of a collision.
And just before I continue, because I keep doing this, and I've had people ask me this before in the past, how do you determine what the correct pronunciation of Karen or Sharon is? I know that everyone has their own personal favorite.
They're both correct, so you are just fine. According to the official documentation, you can say both Sharon or Karen. And it's just that I was trained in the classics and I have a history degree, right? And I studied ancient Greek and Roman history. And it's just really hard for me to break the habit. So I say it the way you would say the mythological figure Charon the boatman. But there is the story about how the guy that discovered Charon has a wife named, I think, Charlene.
Yep.
And so he wanted to name the moon after her, and love is real, so I support them. I just call it Charon because, old habits die hard. They're both fine.
It's so funny because I had heard that story before from word of mouth. That's why he ended up naming it that. But I had never heard someone else say that before since my time working in an observatory. So it's nice to hear that that wasn't just hearsay. That's actually potentially part of the history.
Yeah, it's not apocryphal. It is real. If you check Wikipedia, Wikipedia would never lie to me, and it is real. But so a lot of people in the Pluto community will recite this story to you. So we all agree that Sharon is named for love, and Karen is the boatman of the river Styx.
I mean, as we brought up during our last conversation on the subject of Pluto, there is something very romantic about the Pluto-Charon or Charon system. Not only are they very similar in size and the center of mass in the system is in between the two of them, but they're also tidally locked to one another, doing this kind of cosmic dance. So I think that's very fitting.
Yes, and let me tell you, the initial collision really set their dance off on the right foot. Yes, I'm always saying that the relationship between Pluto and Charon is romantic, and the best part of releasing this paper has been everybody going, actually I kind of see it now.
Right.
So finally, their time has come.
But now we have to get into the whole math of that romance and how that fell out, because the fact that they are so close to each other and the very circular nature of Charon's orbit is rather strange. So we have to do this kind of modeling in order to simulate how this fell out. And usually to do this kind of modeling, we use fluid dynamics, but it kind of struggled to explain the properties of this system. So why would that be potentially inaccurate when it comes to Pluto and Charon?
So the way we typically simulate collisions between bodies that are similar in size, which we call giant impacts or planetary scale collisions, variety of names, we use what we call smooth particle hydrodynamics collisions. And hydro's in the name, right? We're doing smooth particle hydrodynamics because we're approximating astronomical bodies as fluids. The way these codes work is they solve the equations for the continuous flow of a fluid through a medium, which means in practical terms, the bodies don't have fluid strength. So I can build a planet out of particles, which is what I do. But then once you hit it, it's going to behave like a fluid. And in practice, what that means is if you look up any papers that do this kind of work, you'll see the two bodies collide and then experience these massive amounts of deformation as they kind of behave like two blobs in a lava lamp would as they collide with each other. So you get these massive what looks like a planet, it now gets stretched out until it looks like a kidney bean and then pulled apart and they come back together. And the way that previous simulations looked at the Pluto-Charon system set up their collisions this way and found that one of the major things that was necessary for the collision to actually capture Charon as a satellite was that Charon had to come in at an angle, graze Pluto, and then deposit just enough of its angular momentum to experience this full body kind of getting pulled apart, and then it got stuck in Pluto's orbit. But there's a problem with this, which is that Pluto and Charon are not fluids. That's a tough one to really sink in. But it's okay. We don't actually have to simulate them as fluids because work in the last 5 or so years has been taking these codes, which were originally designed to simulate collisions between galaxies. And that's totally fine. Galaxies behaving as fluids, don't worry about it. What is material strength to a galaxy? That question ends up in the realm of like philosophy. When it comes to planets, it's not philosophical. We know the Earth is made of rock, and we know that if you were to go outside right now and punch the ground, the Earth would resist you. That's because the Earth has material strength. Rocks can resist a force that isn't placed upon them. I recommend stopping the podcast now and going outside and punching the ground just to see this for yourself. The same is true on Pluto. Even though Pluto is made of rock and ice and not rock and metal, the same thing is true. Ice has a strength. The reason all of this matters is because, okay, if Pluto and Charon are geologic bodies, then the question becomes, should we treat them like geologic bodies? And this has been a question that's been kind of ongoing in the very niche giant impact simulations side of the planetary science community, because we weren't sure at what scale of impact material strength starts to matter, right? Because we think a collision tipped Uranus over, right? A super Earth hits Uranus and tips it over. Maybe, right? Do people know about that? Anyway, separate answer. In that case, it doesn't really, you can treat Uranus as a fluid, it'll behave like one, and that's fine. But when you get down to the Pluto-Charon scale, it might matter a lot more. And previous research that was actually published just last year showed that material strength starts to matter at around the size of the Earth-Moon collision and smaller. So what we decided to do is implement what's called a strength model into our version of this code. And run the test again, see if Pluto can capture Charon again and what changes about that. And when I say strength model, it's a way of telling the particles that make up Pluto and Charon that we build to behave like the materials we've told them they are. So the ice has to act like ice and the rock has to act like rock. And that is data that we give them that's taken from laboratory tests from the people that squish rocks to see how much pressure they have to be under before they break. Those kinds of people, we're using that data and we're putting them into our simulations.
You brought up something interesting, which is that these kinds of strength models are more useful for things under a certain range of masses and not over. Is that because of just the energetics of larger
Yes.
interactions?
Yeah, right. Because on the scale of the Earth Moon impact, it's so violent that you end up with this global scale vaporization and melting. And oops, if you melt the Earth, that's a fluid.
Yeah.
So the larger the impact, the more violent it tends to be. And at some point, you're colliding objects that are so big that it is feasible to approximate them as fluids. And basically, what the work did was test, basically turning the strength model on and off and saying, does it change the impact outcome? And above a certain size, it doesn't change the impact outcome because the impact is so violent that both bodies melt enough that they behave like fluids anyway. Does that make sense?
Yeah, it totally makes sense. And also makes sense that we wouldn't have to have thought as deeply about this until about this moment, because most of the collisions that we've been thinking about over the course of our solar system have been these larger impacts. But now that we have missions like New Horizons that's going out there and looking at these trans-Neptunian objects, we're going to be finding smaller objects, more icy objects, maybe these contact binaries, and that's a whole different realm of modeling, or at least your research suggests that we do have to think about it differently in order to be accurate.
Oh, yeah. When you go out into the Kuiper belt, everything is moving a lot slower and it's a lot smaller. And it's made of ice. Turns out all three of those things matter.
So how does this kiss and capture scenario play out?
Well, you see. The first thing I'll say is we tried to reproduce the old model where Charon comes in at this angle and grazes Pluto and then gets captured. Well, that doesn't work anymore because it turns out when the bodies behave like rock and ice instead of like fluids, Charon just kind of grazes Pluto and just keeps going and says, goodbye. I'll miss you, but I have to keep going in the solar system. And we said, well, that can't be what happened because Charon is there. So instead, we had to do a lot of testing and found this new regime, which we call kiss and capture, not just for fun, because it is descriptive of what happens. Charon comes in at a shallower angle this time. And when Pluto and Charon collide, they partially merge. So Charon penetrates somewhat into Pluto, digs into Pluto's icy mantle, and the two bodies merge for a little bit and co-rotate as a single massive contact binary, kind of like if Arikoth was huge. But here's the thing. In these simulations, Pluto's already spinning before Charon hits it. Planetary bodies tend to do that. And if it's spinning rapidly enough, Pluto is able to effectively push Charon back off so that it establishes itself as an independent body. And because Charon just kind of slowly separates from Pluto, it ends up in this nice circular orbit, orbiting Pluto, from which it starts to slowly expand to its current position. And so we call this a kiss and capture because there is a period in which the two bodies collide and are one body. That's the kiss. And then Karen separates and says, okay, I'd like to stay here.
So there's a very specific kind of range of rotation speeds that allow for this, right? Because if it was going way too fast, I imagine Sharon might just fly off, but too slowly and they just stick together and that would be strange. I imagine over time, hydrostatic equilibrium would eventually bring it into one giant circular object instead, or oblate spheroid object instead of this Arikoth-like potato contact binary object.
Yeah, you're quite right. If Pluto spins a lot faster, you can get to the limit of stability for an object of Pluto's size and it will just explode. I ran a simulation where I tested, okay, what would happen if Pluto was spinning with a period of 2 hours? So one day on Pluto would be 2 hours in the simulation. It just exploded before Karen even got there. And I was like, well, that didn't happen either.
But also a really interesting thing to note. I think a lot of people have been kind of baffled by a lot of these asteroids we're seeing with these tiny little moons that are also these contact binaries, and that as well could be because of their spin rate and them
Exactly,
flying
yeah.
stuff off into space. So this is pretty key. But what kind of range of spin rates allows for this to happen?
Pluto needs to be spinning pretty fast, but not too fast. So, if you've heard of the dwarf planet Haumea, it is spinning pretty rapidly today, which is partially why it looks like a loaf of French bread. And it has a spin period of 4 hours. So, a day on Haumea is 4 hours. Pluto needs to be spinning at close to that, or maybe even faster, so close to 3 hours. If Pluto is spinning even at a period of 6 hours, Charon collides with Pluto and they merge as one body. Pluto doesn't have the angular momentum to push Charon back off.
So
Yeah.
there's the spin rate of these worlds, but there's also the impact angle. How does that affect this?
Well, if you, again, build yourself a little picture in your mind, you can imagine how impact angle might affect things quite a lot. In a lot of the images that we see of asteroid impacts in popular media, and also if you go to conferences, a lot of times what you'll see is an asteroid hitting something head on, right? So just like the asteroid forms a 90-degree angle with the surface and just falls straight down and hits the surface, right? Well, it's not necessarily realistic for that to happen. If we actually work out the math, and this actually works out to basic geometry, the average angle at which something will collide with something else in the solar system is 45 degrees. For the same reason that a right triangle can have two 45-degree angles. It's the most efficient. It's the in-between one. It's a Gaussian distribution. I will stop there. But so it's unlikely that an asteroid directly punches down to the surface. It's also equally unlikely that you completely graze the surface as well. So that was actually one of our motivating factors, right? Because the previous iteration of the Pluto-Charon capture involved Charon coming in at quite an angle, what we would call oblique. So where Charon is more grazing, and it has to do that, right, in order to be captured. But what we found in our scenarios is when both bodies are simulated as actual geologic creatures, that you can do this at 45 degrees, which is the most likely angle for this to happen. And we reproduced it about 14 times for impact angles of between 40 and 65 degrees. So what we found is like anything close to the mean impact angle of stuff hitting each other in the solar system, this could happen. Kiss and capture could work.
And when they actually contacted each other, they became this kind of giant contact binary object. About how long do you think that could have lasted?
Not very long at all. That's the fun part. So Pluto and Charon collide and merge, and that initial process is quite quick, takes less than 5 hours, and then they co-rotate as a single body for another about 10 hours, and then Charon starts to slowly separate. By about 30 hours after the initial impact, Charon is back out there by itself, establishing a stable orbit. Everything is done in less than 2 days.
That's wacky and
Yeah.
really cool to know. Although I bet it's a little harder to pin down when in the history of the system this actually happened versus how long it took.
Yes. The reason why it's so hard to pin down is basically the Pluto-Charon collision and the capture of Charon is kind of the starting point for the system in terms of how we think of its geologic history. That's because it's such a disruptive event, not as disruptive as the Earth and the Moon, right? But still disruptive enough that the surfaces of both bodies get completely covered with new stuff because Pluto and Charon exchange material between the two of them during this collision. So at the end of it, you have new surfaces for both Pluto and Charon onto which geology then accumulates and you build the geologic features that we now see. So that's kind of the final reset before Pluto and Charon then evolve from there. And so after that, then some point later, you have the second impact, and then
The
Sputnik
splat.
Planitia forms, right? Yeah, then the splat happens. And so because of that, we can just say that this is the earliest thing that happened for Pluto and Charon. We can make some more guesses about that, but the easiest way to kind of try to put a timestamp on it is to think about realistically when planet collisions were happening, when two bodies were hitting each other. And based on that, we think it happened at some point early in the solar system's history, similar to when the Earth and the Moon collided. So this would be in the first tens of millions of years after the solar system formed, back when all of everybody's orbits were a little more chaotic, when the giant planets were still forming and thus migrating around and could shove around the smaller bodies such that you could have two bodies in what is now the Kuiper belt get pushed onto a colliding course with each other. It's much, much harder to do this today because everything is really spread out on the Kuiper belt today. There's just too much empty space. Stuff isn't really hitting each other right now. But early on, very different story.
We'll be right back with the rest of my interview with Adeene Denton after this short break.
I'm Jack Corelli, Director of Government Relations for the Planetary Society. I'm thrilled to announce that registration is now open for the Planetary Society's flagship advocacy event, the Day of Action. Each year, we empower Planetary Society members from across the United States to directly champion planetary exploration, planetary defense, and the search for life beyond Earth. Attendees meet face-to-face with legislators and their staff in Washington, D.C. to make the case for space exploration and show them why it matters. Research shows that in-person constituent meetings are the most effective way to influence our elected officials, and we need your voice. If you believe in our mission to explore the cosmos, this is your chance to take action. You'll receive comprehensive advocacy training from our expert space policy team, both online and in person. We'll handle the logistics of scheduling your meetings with your representatives, and you'll also gain access to exclusive events and social gatherings with fellow space advocates. This year's Day of Action takes place on Monday, March 24th, 2025. Don't miss your opportunity to help shape the future of space exploration. Register now at planetary.org/Day of Action.
It does feel rather strange that we already know of at least two large collisions in the history of this body, Pluto, which is not very large. When you think about the distances between these things, that actually is seemingly irregular, or at least spectacular.
Yes, many people have commented on the fact that it's just like, how does it happen twice? How does Pluto have a bad day two times in a row? Well, the easiest way to explain all of this, geologically speaking, is for Charon to have come in and hit Pluto, and Charon has a radius of around 600 kilometers. So that's pretty big because Pluto's radius is around 1,100, close to 1,200. So something half the size of Pluto comes in, hits it, and then gets captured. Bad day. Then you have to form the splat, and that body is about half the size of that. So you have two really big bodies that come in and hit Pluto, separated by some amount of time. We don't know how much time there is between the first collision and the second. But again, they both make the most geologic sense with what we're observing on the surface. I should note that we know that there is some amount of geologic interval between the two because Sputnik Planitia, Pluto's heart, is not the oldest thing on Pluto's surface. It's the second oldest thing on Pluto's surface. There's one older thing, and that's this ancient ridge trough system that we observed running north-south along Pluto. And Sputnik Planitia splat right on top of that, overprints it. So we know that it's younger than that. So Pluto captures Charon, and then ... stuff happens. Pluto experiences some sort of period of global extension to form this massive ridge trough system, and then it's time for impact number 2.
So it's quite possible that this impact helped create this ridge trough system or other features. Charon has these kinds of fracture-like features. So maybe those things that we haven't been able to explain could be potentially explained by this close encounter between the two.
Oh, potentially, yes. There's a lot of debate as well. We love to debate in the Pluto community because we have so little information that you can just have debates about a lot of stuff, similar to going online. And one of the things we don't know is when Pluto and Charon first formed, which controls their heat budgets. And if you don't know how hot Pluto and Charon were when they formed, you don't know how long Pluto had an ocean and whether it still has one today. Because stuff like that depends on how much heat sources you got. If Pluto and Charon formed really early, then you have those early quick decaying radioactive isotopes that can provide a lot of early heat early in the solar system. One of those is aluminum-26. That's the big one. And if that happens, then Pluto starts out pretty hot. It's really happy. You then form an ocean early on, and it can persist to the present day. But that means Pluto and Charon have to come together really fast in order to do that, which might be a little bit difficult. And the people that study the accretion of planetesimals into planets in the solar system have found that it would be easier if it took Pluto and Charon a little longer to bake, which is a poor analogy because if Pluto and Charon formed later, they actually are colder because they don't have access to those radioactive isotopes. They just have the other ones that take longer to decay and don't produce as much heat. And if that's the case, then they start out pretty cold and then Pluto can eventually form an ocean down the line. But here's the thing. Check this out. The impact between Pluto and Charon deposits a lot of heat into the system. We found that it can raise the average temperature of Pluto's ice shell by around 80 Kelvin, which doesn't sound like that much, right?
But really though, that's actually
yeah,
quite a bit when we're talking about space temperatures.
yeah, well, especially when we're talking about ice. A lot can happen for ice in 80 degrees change, and that could push, say, an ice shell that's 200 Kelvin at its base to 270 and over. So you could start melting the ice shell. So Pluto might start cold, and then this impact happens, and you experience this bulk heating that could drive potential initiation of melt in Pluto's interior to form an ocean. And then the other part of this is tides, right? The moon raises tides on the Earth and vice versa. And the moon is a lot farther away than Charon was from Pluto at the end of our simulations. At the end of our simulations, Charon is only between 2 to 3 Pluto radii away. It's right there. What that means is massive full body tides. Pluto and Charon will respond to each other and effectively flex in response. And a lot of that deformation will get transformed into heat. And you might have a way to produce a long-lived heat source for a while as Charon starts to migrate outward. And what that means is that, yeah, after that point, you have all of this heat and you might form an ocean. And then as Pluto then slowly starts to cool, you'll get expansion features like the ridge trough system.
That could also explain some other things for me. And the potential subsurface ocean is one thing, but there's also this surprising cryovolcanism. There are just some things going on Pluto that make more sense if we have this internal heating.
Yes, and now we have a way to reconcile Pluto having a lot of internal heating without having to rush to form it really on at the start of the solar system. So this might be a way to make everything line up.
But that also means that potentially one side of Pluto and one side of Charon were experiencing this kind of prolonged frictional heating in the early stages, and now they're tidally locked. So
Yes.
could there be, as with the Earth-Moon system, a distinct difference in the composition and the geology of one side of Charon versus the far side?
Many people have asked this, and the problem is that our pictures of the far side are pretty bad.
Right?
So, yeah, sure. That could totally happen. It's just really difficult to prove. I saw someone suggest once that Charon has this massive canyon system along its equator, basically, and someone said, Adeene, could that have formed from a giant impact on the other side? Sure, but we can't see the other side. So, yes, you could possibly produce some sort of hemispheric dichotomy between the sides of Pluto and Charon that are facing each other and those that face away. But I would love to return to Pluto with an orbiter to try to prove that or not.
Really, though, I mean, after learning about the history of its impacts, that could be really valuable. We'll get into this in a little bit, but there are so many implications for understanding how these objects have evolved over time that could teach us a lot about how our solar system formed. But you did say that Charon and Pluto were much closer and that it kind of moved away from Pluto over time, as many systems with tidal forces do. But how did Charon end up in this rather circular orbit?
That's a factor of the way that the kiss and capture works. So, okay, let's go back. We're going back in time. Charon's coming in from the side, it's going to hit Pluto. Pluto is spinning. They merge, but only a little bit. And the reason they only merge a little bit is because Pluto and Charon are relatively strong. So Pluto is basically able to resist Charon's penetration. So Charon only gets a little bit of the way into Pluto's icy mantle. What that means is that most of Charon lies outside of the co-rotation radius of both bodies. So they're co-rotating as one. They've merged and we say co-rotating because they're rotating as one body, right? But the problem is that most of Charon lies outside of the actual center of mass of the system at this point, and it can't keep up with Pluto. Pluto is orbiting relatively rapidly, which is why this whole thing happens in the first place, and Charon kind of lags behind. So because Pluto spins faster than Charon can follow, the two bodies start to slowly decouple. And what happens is you're introducing a torque. This is this is physics. This is mechanics, right? Pluto, you have this angular component, right? And Pluto starts to torque Charon outwards. And because of that, it establishes this close circular orbit. The reason that the previous orbits were so eccentric is because Charon came in at an angle and then passes Pluto, right? They don't, in the fluid situation, they don't merge. Charon hits Pluto and then starts to deform like a blob in a lava lamp, shears across its entire dimension. So the entirety of Charon gets almost pulled apart, and then it's able to snap itself back together and then come towards Pluto again to get captured as a satellite. But because of that whole process, it's pretty elliptical. You end up with a more eccentric orbit that would then have to circularize. In this case, because Pluto and Charon are literally connected to each other, when Pluto kind of shoves Charon off and lofts it into orbit, the orbit is relatively circular. Does that make sense at all?
Yeah, actually, that does make a lot of sense. Having that contact between the two is like key, and understanding that it didn't do the full like molten shred is going to change the way that
Yes.
happens. That makes sense. But I'm sure that during this impact and even during their little kiss and capture moments, Charon probably lost some of its mass during this process.
It did, but not as much as you would think.
Hmm.
So in the previous case where Charon literally shears itself apart, it loses a substantial fraction of its mass to debris. But what we found is when both bodies have material strength, they retain their structural integrity. So they collide with each other, and most of the mass loss is actually Charon leaving some of itself behind in Pluto. It loses a small fraction of its core, so its rocky core gets stuck in Pluto's mantle. And similar to the case of the splat, right? If you leave some rock in Pluto's icy mantle, it's going to slowly sink down and be added to the top of Pluto's core. And then Charon also loses some of its ice, both to Pluto, but then also as the two bodies rotate and Charon's spinning, trying to keep up with Pluto, they're connected. Some ice gets stripped off of the far side of Charon that's not connected to Pluto and thrown out into a debris ring. And you can't see this in the images of the paper or the videos because we're zoomed in so close on the system. We're not looking at that. But if you zoom out, that debris, most of it is actually captured in the system. Some of it's going to come back and recollide with Charon or potentially Pluto, but the rest of it gets established as kind of a debris ring that's outside the orbit of Charon.
Does that explain the other four moons that are in the system?
Maybe Pluto has four other moons, but they're really small. And when I say really small, I mean like multiple orders of magnitude smaller than Charon. I think the mass of Charon is like 10 to the 21 kilograms. So Pluto is around 10 to the 22, Charon is around 10 to the 21. This is important as a good means of reference, right? Those are similar. Those are close together. Well, Nix, Styx, Kerberos, and Hydra are on the order of 10 to the 15 to 10 to the 16 kilograms. That's a lot smaller than 21 and 22, right? We're talking multiple orders of magnitude smaller. These little guys are potatoes. This is the Phobos and Deimos of the outer solar system type morphology you're looking at, these little guys. And I don't say this to degrade them. I think it's great. I think we should have icy potato moons as well as rocky potato moons. And I think it's so beautiful that New Horizons captured these images of them. That being said, it's a resolution issue for my simulations. I cannot currently gain enough computing power to run these simulations at high enough resolution to adequately resolve moons that small. What I can say is we put stuff out into a debris disk that could then coalesce to form these moons, but I cannot definitively say at this time because I need the biggest computer you have. If you give me the biggest computer you have, I promise to only use it to have Pluto and Charon kiss each other.
Not for evil.
Not for evil. I am a force for good.
So they come in, they do this kiss, they're now in this nice little circular dance. But in normal cases where we have these very kind of apocalyptic, smashy type collisions, it really changes the chemistry of the system. The energetics, the way that everything mingles together can really change some things. They'll change each other. But in this case, we've got this kind of slow rolling, a little less energetic kind of collision. You did say some of the material comes off of Charon and ends up on Pluto, but how much of these objects have been altered by this process? And can we still consider them to be mostly the same pristine material that we see in the early solar system?
That's why the paper is called Capture of an Ancient Cairn Around Pluto, because the two bodies don't experience this intense amount of deformation that we saw in the cases where Pluto and Charon were approximated as fluids, but they also don't experience the intense drama of the Earth-Moon collision where stuff is getting melted, stuff is getting vaporized. Remember, they're hitting each other at 1 kilometer per second. Like I said, the average increase in temperature in Pluto's ice shell is around 80 Kelvin. It takes solid ice to liquid ice, which we also call water. It can drive the formation of an ocean on Pluto, but in terms of more drastic changes, it's just that the collision isn't that dramatic. Pluto and Charon collide with each other, trade a little bit of material, but they retain their initial morphology and their initial composition. So Charon comes in with whatever core size of rocky core and ice shell that it has. Pluto starts off with whatever rocky core and ice shell that it has, and then they collide. Charon leaves a very small fraction, less than 5%, in some cases less than 1% of its mass on Pluto, and loses some of it to debris. But mostly what you started with is what you ended with. So yes, these two bodies are likely, if this is the case, if this is what happened, if Pluto captures Charon with a kiss, then both bodies form in the early solar system, and we're looking at the relics of that initial formation process.
It would be so cool to go back out there and check out the composition of both those bodies in full spectrographic glory, but also all the moons and both of their sizes, because I think this could teach us a lot about the way that the system formed, but also knowing that they're mostly unchanged since the beginning of our solar system. That is pivotal information that can teach us a lot about the way that our solar system formed.
Oh, absolutely. And the thing to keep in mind is that Pluto and Charon aren't really alone out there in the Kuiper belt, right? That's the whole reason Pluto isn't a planet anymore, is because there's other Kuiper belt objects that are similar in size to Pluto. But the thing is, a lot of those also have pretty big moons. 8 out of 10 of the largest Kuiper belt objects have a little guy there. They have a large mass fraction satellite. There's Eris and its moon Dysnomia. There's Haumea and its two moons, Hiaka and Namaka. There's Orcus and Vanth. Nobody thinks about Orcus and Vanth, but I do.
Well, you did in this paper as well.
I did in this paper.
You applied this modeling to Orcus and Vanth. Why was that the example that you went for?
Just because I really want to raise the profile of Orcus and Vanth with the community. That's not true. Well, it's kind of true. But Orcus and Vanth have this cool thing where they have a similar mass ratio to Pluto and Charon. They're just a lot smaller. Orcus and Vanth are about 40% the size of Pluto and Charon. So it raises an interesting test case of, okay, if 8 out of 10 of the largest Kuiper belt objects have large mass fraction satellites, does kiss and capture happen every time? Is this how it happens, or does something else happen and this is just coincidence? So what we did was scale down Pluto and Charon to 40% of their mass and run back the tape. And what we found is this same process, kiss and capture, could work for Orcus and Vanth, which are a much smaller system. And that's a pretty promising finding to suggest that this process, kiss and capture, could have happened all over the Kuiper belt in the early solar system.
And we've seen so many of these contact binaries, maybe they just weren't spinning right to actually separate.
Exactly, yeah. Yes, Arrokoth is such a promising look at other contact binaries in the outer solar system.
Yeah, that's cool. But there's still a lot that we don't know about that system. And as you said, you only have so much computing power in order to do this. So what aspects of this kiss and capture process do you think need further exploration?
Well, it's less the process, though. Please call in, give me your computers, and I will blow up Pluto with them. It's less the kiss and capture process, which we're slowly starting to understand, but what happens after, right? The key to understanding whether kiss and capture is what happened is being able to better tie it to the information we have about the geology of Pluto and Charon today. And to understand that, we have to pick up a few more missing pieces. At the end of my simulations, it's been about 60 hours. It's been a few crazy days for Pluto and Charon. And Charon is slowly migrating outward. But the problem is, Charon's going to migrate outward on geologic timescales. I'm talking thousands of years, right? And my simulations are designed to handle impacts that happen in a matter of seconds to hours, so we can't track what happens after. The next step is to say, okay, what are the tidal forces like on Pluto and Charon? How does that affect their thermal history over geologic time as Charon starts to slowly move outward? And can we tie that to what we're seeing on the surface of Pluto and Charon today? So the next step is actually to look beyond the initial kiss and capture to the geologic and dynamic implications it has for Pluto and Charon.
What are some of the geologic features or things that you would be looking for in order to understand that better?
Well, we want to understand at what point Pluto's ocean forms. And to do that, we would want to look at the timing of the formation of the giant ridge trough system. And then from there, what happens when Sputnik Planitia forms and you collide with Pluto again and how that changes Pluto's interior structure. Because if it was a splat, then Pluto doesn't need to have an ocean at all, right? So maybe Pluto cools off too quickly, maybe not. Hard to say, right? And then, of course, the other piece of it is Pluto's putative cryovolcanic spots that it has some to the south of Sputnik Planitia, some to the west. And determining whether, okay, is there enough tidal stresses going on? If you heat Pluto up and then you put it under a lot of tidal stress, is that enough to drive liquid water up through the ice shell to actually produce that cryovolcanism? So this produces another interesting series of test cases to see, okay, now that we've got more stresses than we thought about before, does it make it easier for something like cryovolcanism to happen or not?
Do you plan on pursuing this kind of research, or do you have other things that you would like to blow up in your simulations?
I'd like to take a look at some of these other systems that are similar to Pluto and Charon, but a little bit different, right? And just to really see if kiss and capture could work all across the Kuiper belt would mean looking at some of these other systems that we don't understand as well, like Eris and its moon Dysnomia. Eris is more massive than Pluto, but its moon is less massive than Charon. So you have a system where Eris has a lot more rock, but its moon is smaller and has a lot more ice. So does it still work for that system? What about Haumea? Haumea has two moons, a ring, and a collisional family, which is what we call it when you hit something and it releases a lot of debris that then travels outward throughout the Kuiper belt. It's got all of that going on. Does kiss and capture work in that scenario? Those are the kinds of questions I'm interested in, though I'm also really interested in the geologic evolution piece. I'm not a dynamicist. I cannot do tides. I am collaborating with other people to try to take that part of the work forward. But I'm so curious about how this worked all across the outer solar system. And ooh, this is like a fresh idea, like straight off the dome. So this might sound hilariously bad. But one of the things I was talking with someone about the other day was, you know how Neptune captured Triton?
Yes.
Well, Triton used to be a binary, or so we think. So, yeah,
Really?
so we
I haven't
think
heard this.
apparently, the dynamics are much easier if Neptune is able to, this is not the technical term, if Neptune is able to yoink Triton out of a binary.
I never even considered. I mean, there's so many strange things about Triton. The fact that it, rotates the wrong direction. All these interesting things. But
Yeah.
yeah, now I'm gonna have to call up someone who's an expert on Triton to learn more. But again, another system we need to go back to get more information on.
We really do. Triton. So few images of Triton.
But another one of those worlds that just it could have a subsurface ocean, is doing all these strange things. Probably a captured Kuiper belt object, and now I'm learning might have an evil twin out there or an evil friend just cruising.
Yeah. Got pulled away from its friend.
Right?
It's lucky it wasn't Pluto and Charon. I'm glad they're together.
Me too. And now we know more about how they came to be in this strange and very cute relationship with each other.
Yes, and there's a lot more to learn about the system. So everybody lock in for the long haul for the Pluto orbiter that we will one day launch.
Whether or not it's in this decade or 100 years from now, it's going to happen. And we're going to learn more about these systems, and it's going to blow our minds.
It really is.
Well, thanks for doing this research and also for just having one of the coolest jobs ever, being able to just sit around blowing up worlds to see if we can piece together the history of our solar system is just such a cool way to spend your time.
I really enjoy it. I'll keep blowing up various outer solar system bodies until someone tells me to stop. So please don't tell me to stop. This is my passion.
Well, let me know when you come back with some cool new information about the way that any of these other objects formed, because I'm in it now.
You got it. I think I'm turning my eye to the Uranian satellites and the Saturnian satellites, so I'll report back. There's a lot of weird stuff going on in there. The moons might have hit each other, so
So cool.
lots to learn.
Well, thanks for coming back, Adeene, and good luck in your future research blowing our minds with the weird history of the solar system.
Thanks for having me.
I always thought Pluto and Charon were adorable, but now that I know a space kiss and capture were involved, I nominate Pluto and Charon for cutest couple in the solar system. It would be a really interesting scenario if they actually were a contact binary for a time. Here's Dr. Bruce Betts, our chief scientist. We'll chat a little bit about other contact binaries in our stellar neighborhood in What's Up. Hey, Bruce.
Hi, Sarah.
So before we get too far into this one, I want to ask you, do you pronounce it Sharon or Karen?
So I usually pronounce it Sharon, but sometimes it's Karen, sometimes hey you, sometimes no, don't take my coins. It's an obscure reference to mythology and the river Styx.
Really, though, I mean, there are so many depictions of this character through different bits of media, and in many video games, I've had to pay that guy some coins. So always keep some coins in your pockets just in case. But
it's a really cool world. That's such a fascinating system, and more
it just
fascinating.
keeps getting weirder, dude. I knew that Charon and Pluto, they had this beautiful kind of relationship with each other, the way that Tholins off of Pluto are blowing onto Charon and painting it red, and the way that they're tidally locked. There's so much to love about this system. But this is the second time I've had Adeene Denton onto the show, and now I find out that, it depends on whether or not this type of modeling for that system is correct. But what their team's numbers suggest is that Pluto and Charon were a contact binary before they flew apart. and that is absolutely bonkers.
What you talking about, Willis?
I know, right? So apparently they had this an encounter with each other. They smashed into each other for this very short amount of time. They became this contact binary, and then Charon spun off and went into this circular orbit and moved away, and now they're in this beautiful little relationship with each other. But for a hot second there, things were really weird. That's
really weird. It's still pretty weird that they're fully tidally locked, facing the same face to each other all the time.
Right? It's wacky. I really enjoyed reading through this paper. And as with all of these things, I mean, we've only flown by Pluto once. There's only so much information we have about that system. And we're making suppositions based on modeling and parameters of material strength and all this kind of stuff. So it is quite possible this wasn't the scenario. But, a lot of the math that comes out of it and the explanations for how the system works is way more consistent than any of the previous modeling. So I like to imagine for a second, what if there was this moment in solar system history where they were a contact binary? And what could that teach us about?
And then they were, and then they weren't.
Exactly.
Whoa.
And I've just had this kind of little moment with contact binaries over the last year, mostly because of the Lucy mission that's going out to the Trojan asteroids and that discovery of Dinkinesh, of Dinkinesh's tiny little double-lobed moon. They're not really sure how this double-lobed kind of moonlet began, and it's quite possible that the material that made it was flung off of the asteroid and then turned into two objects around the asteroid and then came back together. So I think there's a lot of interesting physics that's going on here with these smaller asteroids that are spinning off material, and I'm wondering if we're more likely to find these kinds of double-lobed moony things around maybe these smaller scale asteroids. Right?
Interesting.
We
No,
wouldn't know
there's
until we look at a bunch of them.
they're just weird, or I should say, non-intuitive physics going on with small asteroids or that type of body, because we're used to Earth, our big friend with big gravity, and you get those little rocks that have gravity enough to hold things together, kind of, but hanging right on the border. And so you end up with these weird things like rubble piles and contact binaries.
I actually mentioned this during the show that if something is big enough, you end up with this situation where under hydrostatic equilibrium, it will turn into a ball, right?
Yes.
In this situation, these objects are too small, but it occurs to me that I did not define what hydrostatic equilibrium is or why larger objects are more likely to turn into ball objects instead of just being these kind of double-lobed weird potato moons.
So, yeah, well, hydrostatic equilibrium, the fastest thing on the podcast is to not go into the physics details, but go into the conceptual physics, which is eventually when you get something big enough, the self-gravity that's pulling everything towards the center ends up rounding things out through whatever process of landslide and shifting and things, because you have enough gravity that everything wants to be relatively equipotential, experiencing the same gravitational force. So that happens depending on the strength of the material, but asteroids, it's up in the many hundreds of kilometers in diameter. And so that's why all the planets are roundish. And so it's a balance between the gravity and the strength of the material, and that's kind of the hydrostatic equilibrium thing. But you get anything under that, and you end up with these potatoes, and potatoes looking weird and joining together, and that's why we get all the different shapes in the asteroids. Although we're seeing some very similar shapes in some of them, which is a physics thing too, presumably.
Can't wait until I have all these images from all of these spacecraft that are going out to investigate asteroids in the coming years. I'm sure we're going to find some even weirder potatoes out there.
That's the goal of the space program when it comes to minor planets, small bodies, weird potatoes.
Someone needs to make them a sticker. Anyway.
Okay. So are you ready for some fun?
Let's do it.
I mean, we've been having fun, but we go on to random space fact.
Ruh-roh, Raggy.
So there are some funny terms in astronomy and planetary science, and one that I came across recently that is mostly official, but not really, is vampire stars. Are you familiar with
Vampire stars? No.
And as I say, it's a little unofficial, but it's the concept that they're sucking the life out of a star with them. So they're in a binary star system. It could be like a white dwarf that's basically an expired star. That's not the technical term. It's used up its fuel. It's not doing nuclear reactions, but it's hanging out near some other star, or maybe red giant, and it ends up setting up a situation where it's pulling material off it, and then it can. And so they use the term vampire star. Well, at least the wackier people do.
I love that. That is such a descriptive term. And I'm going to have to bring that up the next time I'm talking about Type 1a supernovae.
There you go. There's your example of vampire. So that's why I say they're more official terminology, I believe. But I enjoy vampire star.
That's awesome. We're going to need some fan art around the Halloween time.
Hey, everybody, go out there, look up in the night sky, and think about how big a wooden stake you'd need to drive through a vampire star to kill that sucker. And, they kind of sparkle. They're one of those sparkly vampires. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio planetary.org. Or, if you're a Planetary Society member, leave a comment in our Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our dedicated members from all around the world. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.